And that looks like a stream that's up. So that's a good start. Good evening, everyone. My name is Matthew. Welcome to the SFU Trottier Observatory Starry Nights live stream. We actually have some clear skies. We didn't know how that was going to go, but look at that. We actually have some skies up there. We can actually see what's going on. So we figured, well, we better open up that dome and connect with all of you out there in the universe to go look up at the stars. Joining us tonight as moderators, we have both Kyle and Xena. Hello, Kyle and Xena. Thank you for moderating tonight. And to get things started, I actually have a special guest to introduce. We've never had a guest on the show before, and tonight we do. So I've got a website up right now. It's called the TNG Project, tng-project.org. Now, when we are looking up at the universe and trying to understand what's going on up there, we're trying to sometimes understand what's going on timescales of billions of years. So how do we know what happened in the distant past or what's going to happen in the far future? Well, one of the ways that we do that is through simulation. And simulations of massive objects like galaxies can be created on computer systems that'll show us what could happen over billions and billions of years. Once we understand the physics of an object and we plug it in, we can simulate it. And so I have a guest today. His name is Kelvin Lee, an SFU science student who is working on some of those simulations, and he's joining us now. I even have a picture of him. Hello, Kelvin. How are you doing?
Hi, Matthew. Thanks for having me here.
You are very welcome. Thanks for joining us. It's cool to talk to people who are actually cranking out the science on learning what might be happening in the far future. So tell us about your research. What's going on in the future of space, and what are you trying to figure out?
Okay, so in this project, we aim to see whether galaxy crunching, that is like the galaxy stops forming stars, has any effects on its density, like whether the galaxy would go compact when they are at the end of their life cycles. So we're using a project data called Illustrious TNG, which stands for like the next generation.
Yeah, I understand that's a Star Trek reference, right?
Yeah, I like Joanna mentioned to me that's a Star Trek reference too. So we use all the available simulation data and then sample all the available galaxies. And these simulation data help us to understand when and how the galaxy evolved into the structure that are observed in the night sky, and to make predictions for current and future observations. So this is a computational and a statistical way to test out our hypothesized correlation.
Cool. So I was looking, I'm going to scroll here through the project website, and one of them has an example of like a real versus simulated galaxy. So this one has M104, which I think is a Sombrero galaxy. So in the top left corner, what people are seeing here, that is the top left corner is the actual galaxy. And then the others on the right are all computer simulations. Those are simulations trying to create an actual galaxy to then see what would happen to it in the future. So your research is looking at the kind of the evolution. Once star formation has stopped, what did we expect was going to happen?
Yes. So as you know, like galaxy, they have like elliptical and also spiral galaxy, and then like this shape of the galaxy usually determines like the age of the galaxy in the universe. So the spiral galaxy, which gets more blue young stars, are more new in the universe, and then the ellipticals are almost at the end of their life cycles. So we're looking at like those simulation data quantities, like the galaxy specific star formation rates, and then the center mass density, black hole central black hole masses, to see the correlation of crunching and compaction. And some might ask us why using black hole masses as a quantity of compaction, because like in the Illustrious projects, the black holes are the main cause of they're responsible for the crunching of the galaxy. So consider like a galaxy with finite size and finite resources. When a black hole forms in the center of the galaxies and grows massiver, it sucks away and also blew away a lot of their resources, their gas, and then its gravity sort of pulled the remaining gas and stellar mass closer. So the growth of the black holes contributes to the increase of galaxy central density, And this is very important because like in actual observations, it's extremely difficult to measure the black hole's mass. So like imagine like how long it took us to take the first image of a black hole.
Yeah.
So we often use the central density as a proxy for the black hole masses and somewhat interuse the two quantities.
I'm bringing up that picture that you're talking about, the actual image of the central massive black hole that we took. The first time we ever imaged a black hole wasn't only till a couple of years ago. So basically what you're saying is that our understanding is that these black holes starve galaxies in terms of their ability to form new stars. So did we find a correlation then between the starvation of the galaxy and then its compacting afterwards? What did your simulations reveal a correlation there?
So what we reveal is like the in-between stage of a spiral galaxy and also an elliptical galaxy. So we only know like these are the majority of categories of galaxy out there, and we have no idea what's the in-between stage of these two. So
Okay.
what sort of progress a spiral galaxy goes and then they change it into an elliptical galaxy. So we don't know. We are trying to form a story to tell how it gets there.
Okay, did we find an in-between stage then? Do we find an intermediate area between those two stages of galactic evolution?
No. So like the hypothesis I just mentioned. So we want to see if the galaxy, when they go crunching, they will also go compact,
Okay.
getting closer together. But in our analysis and simulation, from the simulation data, we don't see a strong correlations of like these two events happening close together. So we were expecting sort of like a 2 point, like the difference of the time difference between these two events would be around like 5 billion years. But we will see in some of my results, the two graphs I sent, they are having like a difference of 10 billions of years of these two events happening.
Okay, so probably then maybe not as related. Unless we have to, is this just a matter of not enough time? Like what if we push the simulation another 15 billion years or 20 billion years?
It's not a matter of time. It's probably tell us something else. I mean, in science, there are so many unanswered questions. So this information's presented to us may not be able to help us to answer our question, but it might be crucial to answer somebody else's questions and somebody else's researches.
That's cool. So that basically what you're saying is that it's important in science to say, I don't know, but here's what I have learned so that someone else might be able to find that out.
Exactly.
All right. So we may not know that intermediate stage yet of quenching an elliptical galaxy formation, but we've generated more data that way. You sent me a cool video. So what is this video that we're looking at, Kelvin?
Okay. So if you're looking at the video right now, focus on the galaxy animation at the top left corner. So it shows the stellar density, and the blue dots in that animation representing the young stars in that galaxy. Look at how they change over time. So yeah, at the those young new star are suddenly disappear. And if you look at like the rest of the animation, you will see several sudden bursts of outflowing gas. That is because of the central black holes. It is blowing out most of the gas required for star formation, and without the gas, the galaxy cannot produce more new stars, and then so it goes into a crunching process.
So, Kelvin, where's our galaxy along that stage of evolution? Like, is our black hole, has it been doing anything recently? Is it quenching star formation in our galaxy?
Our Milky Way is still fairly young, so I mean, like it's just doing like this sort of process like every single day, but our galaxy still have fairly large amounts of gas for the star formation process. So no, like we are not at that stage yet.
So are our galaxies still alive? It's not quenched or squelched.
Yes,
Awesome.
definitely not drenched.
So Kelvin, you're a computer scientist, right? So
Mhm.
why focus on this area of research? What got you into astronomy? Why do you want to be looking at stars on the screen in a simulation?
Well, so I always found like astronomy and physics very fascinating subjects to learn and study. And when I was a kid, I loved watching like documentaries or videos explaining how the black hole was a neutron star, stuff like that. Like till this day, I still enjoy watching them during dinners or before I go to sleep. So, uh, as a computing science student, I always wonder how my skills in like mathematics and algorithms optimizations could be used to contribute into like the understanding to the universe. So and then like back in 2019 when we made the first image of the black holes, like I said,
Mm-hmm.
so I saw a news article about like the people behind the image, and one of them is a female computing scientist. She helped developing the algorithm for optimizing and then processing the observational data to produce the black hole image. And this is sort of like a huge inspiration for me, and this is something I would want to do in the future. And like this research with Joanna gave me a good opportunity to learn astrophysics from her, so kudos to her, and also like practice my skills in processing optimization.
Yeah, I think that was Katie Bowman, if I remember correctly. And I think there's a
Yes,
really cool picture. I'm going to bring it up here. She's like standing in front of towers and towers and
yes,
towers of hard drives
awesome
of the data that they
picture.
coming from all that from that black hole data, which
Mhm.
is really cool. Yeah, so computer science helping us see the universe. Well, that's awesome. Kelvin, if people want to learn more about the work that they're doing, where do they go? Should they check out that the TNG website?
Uh, yes. They could also check out like because this is an next generation projects. They can also go back to the original Illustris. I remember that websites have uh, more visualized galaxy images than the next generation one.
Okay, maybe I can find the website for it. Oh, it's just illustrious-project.org. There you go. That's where a
Yes.
computer can find it. Actually, in my other role at the H.R. McMillan Space Center, we have an illustrious simulation that's formatted for the planetarium dome, and it starts from like the initial formation of photons, and then shows like the collection of matter making the galaxy and the galaxy webs and the cosmic web and stuff, which is really neat. So if people want to play around with these simulations, you can watch literally entire universes form and galaxies form in computer simulation, which is really really cool. Kelvin, so thank you so much for joining us today. We really
Oh,
appreciate it,
you're welcome.
and we'll keep in touch with you to
Thanks for
find
having
out.
me.
Yeah, of course, and we'll hear more about your research in the future. So thanks so much for joining us today.
Thank you.
All right. I have another person that's here today as well that'll be joining me for the rest of the stream, and that is Dr. Joanna Wu. Hello, Dr. Wu. Welcome to Starry Nights.
Hello, thanks for having me here.
And
It's quite a pleasure to be here.
I know it's again it's wonderful that we can actually look up and see anything. So right now the telescope at the Trottier Observatory, you can see in the stream we've got the telescope's in the bottom left, and so we have a live view of the telescope on our stream. If you've never joined us before, you can check it out as it's moving around to different targets. And the top left in your screen is an exterior view of the dome, and right now it is pointed at the brightest thing in the night sky, which is currently the planet Jupiter, which we'll reveal. Here it is. Ta-da!
Wow.
Oh, that's overexposed. Let's
Oh,
go back.
slightly overexposed.
There we go.
Oh, wow. Beautiful. There it is. Planet Jupiter. This is so exciting. I always love looking at anything spacey. It's kind of, pictures are worth, thousands of words, and it's what inspires people to study science. So it
Oh, totally.
inspired me. Pictures of astronomy, it's inspired me to study astronomy. So
One of my
there you go.
earliest memories is looking at the planet Jupiter through a tiny, like, I think it was like a 60 millimeter telescope. Wee telescope. It was my grandfather's telescope. And I remember looking at the stripes. And when Comet Shoemaker-Levy 9 crashed into Jupiter in like the 90s, and everyone had telescopes pointed up to try to see if they could see the black blemishes on the planet from the comets impacting. It's amazing how fast Jupiter rotates, because when I set up the telescope earlier today, the Great Red Spot, which you can kind of see just on the bottom, or like the center right of the planet right now, was a lot more central, because Jupiter rotates in what, like 10 hours or something like that. So it rotates very, very quickly, but you can see the spot on there. It's right here.
Yeah, there it is.
There's the Great Red Spot.
Wow.
Um,
Yeah.
if you have even like a
Amazing.
decent 200 or 300 millimeter lens on your DSLR camera, you can actually check out Jupiter and its moons right on your DSLR camera. You could just punch in with digital zoom and pump up the gain. And if you pump up the gain high enough, you'll actually be able to see Jupiter's moon. So if I overexpose Jupiter a little bit here, and if we back off on the zoom, there are some of the Galilean moons, so-called, because they were observed by Galileo. And when he was studying Jupiter with a telescope, it was one of the first indications that things orbited other things, because we didn't know at that time that Earth was at the center of the solar system. And so he was observing as the moons were orbiting around Jupiter. Now, if you see Jupiter like this, and you see the moons, they're just kind of these bright points, and you want to know which ones they are, you can open up a Twitter account that is called Jupiter Moon Position, which I have open right here. And it updates every so often. I think it's just a script, and it'll tell you in code which of the moons are where. So the J here represents Jupiter, and then you can look at where the moons are located, and it'll tell you G for Ganymede, I for Io, E for Europa, and C for Callisto. And so if we compare that to ours, it's going to be flipped because we're looking at it through a mirror. And so Io and Europa are the two closest on the right side. One is Ganymede, and I don't think Callisto may not be in this view. It may not be zoomed back enough. And it's the one moon that we're interested in right now in our solar system, the search for life, is Europa. So that's this moon right here. You're looking at a moon that might have life on it right now. That's it there. And one of the interesting things about Europa is that we're pretty sure that there is twice as much water on that moon as the entire planet Earth, which is astonishing because we always thought ourselves as like the monopoly of water in the solar system. And so we are planning a trip to that moon in the next couple of years. We want to land on the surface, drill through the ice, and eventually put a robotic submarine down there. One that we've already designed, and we're already studying its usage in our own oceans. And maybe something will swim up to the camera. Maybe we'll find space fish, or space whales, or space octopi, or something. But it's pretty exciting because even if we do find life on a planet like Mars, closer to us, it doesn't necessarily mean that life started somewhere else in our solar system, because Mars and Earth share so much material with each other that gets blown off both planets and floats through space and lands on the adjacent planet. It's possible that life still only started on one of those worlds and then migrated elsewhere. It's possible we actually all came from Mars, or that if there is life on Mars, it came from Earth. But these moons around Jupiter are so isolated that if life is found on one of them, and that could happen within our lifetime. I mean, we're planning these missions right now. That then likely it means that it's a whole other genesis of life, and if you find life in two places in the same solar system, pretty good bet that it's probably elsewhere in space as well.
That would be really exciting to find. Wow. Yeah, so that red spot, that I am so amazed that we can see the red spot so clearly. The atmosphere is actually not too turbulent right now. It's not too bad.
No, it's
Um,
not too bad. Yeah.
yeah. So that, when I was a kid, I memorized a whole bunch of facts about the solar system because I was so into space. I was a really geeky kid. But the
No
world needs
way.
more geeks,
No,
doesn't it?
I don't believe that.
Well, anyway, so I memorized a whole bunch of facts about the planets, and one of the facts that I memorized was that the red spot could fit 3 Earths in it. It could fit Earth 3 times in the Great Red Spot, and now today it can barely fit a single Earth. It has shrunk. The Great Red Spot is a storm. It's a huge planet-sized storm on Jupiter that is shrinking, and so it's quite a thing to realize how much things change, because things in astronomy normally don't change very much, right? They change on the scale of billions of years, but on planets, things can change within a human lifetime. So,
Yeah, pretty astonishing.
yeah, it is pretty astonishing.
All right, we got another favorite planet up in the sky right now, so we're going to go there next. And that is the planet Saturn. So if you haven't joined us before, this is our software called SkyX, and we use it to point the telescope. It's got a whole map of the night sky in it, thousands and thousands of stars, planets, and it moves in real time with the actual motion of the sky and motions of the planet. So we're looking where the telescope is currently pointed is the yellow target. The target we're going to move to is the red one. And this slit here that you see, this higher contrast slit in the image, is where the the opening of the observatory dome is. So right now we're pointed through that aperture in the dome. And so we'll hit slew, which is going to move our target. And if you look, you'll see the telescope moving in the camera and the dome turning at the same time. So that should all be working. And now we should be at Saturn. So let's see.
There we are. So as you can see, Matthew just didn't actually change the exposure until now, and it was quite a bit darker. So Saturn is farther away from us than Jupiter is, and so Saturn is quite a bit dimmer, but it's still brighter than most of the stars. In fact, it's brighter than all the stars in the sky except for the sun. The sun, of course, is the brightest thing. But if you go look in the south-ish part of the sky, you'll see the brightest thing you'll see is Jupiter. It's brighter than all the stars. And then the second brightest thing you'll see right next to it is Saturn. And that's where it is right now. That's what we're looking at.
And amazing other addition here. I didn't save this. I meant to save this photo earlier, but it's very similar to our discussion around Jupiter. There are moons around Saturn that we think may have water as well. One of them is called Enceladus. And I'm just going to bring up an image here because we saw when Voyager was one of the first probes to visit Saturn and take images of it, when Saturn was looking back at Enceladus in the nighttime, here's that picture, on the night side of the moon, it looked up and saw this haze in the background. And at first, the people operating the cameras thought that there was some kind of artifact on the camera. But in fact, that's the water spraying out of this moon, and the mists are being highlighted by the reflection of sunlight that's being diffused by the particles that are spraying out of the moon. So this is one of the direct pieces of evidence that we have that there is water, subsurface water, on moons like Enceladus and Europa, because we've actually seen the geysers spraying out into space. And in fact, the water that's spraying out of Enceladus contributes to the formation of rings around Saturn. So some of those ice particles end up in orbit around Saturn, and so is adding to Saturn's ring structure. And we've actually flown a robot called Cassini, so a probe called Cassini, that was in orbit around Saturn for quite some time. It went through the water to basically taste it, and we found out that the water composition is very similar to our own ocean. So it's got hydrocarbons inside, so those building blocks for amino acids, and also is salty. So it's basically the same soup where we know and understand that life began on our own planet. So maybe it also began in one of these moons orbiting around Saturn.
So speaking of Saturn's rings, they're quite striking, aren't they? So I learned a very interesting fact about them recently. So one thing that I had already known was that the size of the rings from end to end, so from one end to the other, is about the distance between Earth and the Moon. Isn't that crazy?
Wow, that is huge.
It's huge, right? But you know how thin they are? They're so thin that if you compare it to, like, if you had a piece of paper that were as big, the paper would be thicker than Saturn's rings.
Wow.
So if you scaled it, so given its size versus its thickness, the thickness of Saturn's rings is something like 1,000 to 10,000 times thinner than paper, like than a regular piece of letter-sized paper. It's unbelievable. So, we have this English saying that things are paper thin. Well, and we should be saying things are Saturn's rings thin.
Saturn rings thin.
Yeah, I mean, I think that's far more appropriate than paper thin. What do you think?
That's amazing. My understanding is that one of the reasons why there's the rings are so bright is because of the amount of ice that's in them. If you added all the rings together, so if I could reach out with space hands and squish all of Saturn's rings together into a ball, we think it's probably a moon. This could be one of Saturn's moons that was destroyed and ended up all the particles of it in orbit. And like Enceladus and Europa, that moon was probably water-rich, which is why all this ice is now frozen around the planet and is visible. But if you went there, there's no ring to stand on, of course. It's just a whole bunch of tiny, like millions of mini-moons that are in orbit around Saturn. And if you were a dinosaur that loved astronomy and looked up into space, it's possible that Saturn wouldn't have had a ring, because we think the rings are only about 100 million years old or so. So even within the time span of life on our own planet, if you looked up, Saturn would not have had that remarkable feature, which makes it stand out so much. I've got some other cool pictures here. Oh, go ahead, Joanna.
Oh, I was about to say, speaking of Saturn's moons, and just kind of reminiscing about when I first started memorizing facts about astronomy and the planets. So I memorized back in the day that when I was a kid, that Saturn had something like, I don't know, I think it was, I don't remember anymore, 27 moons or something. And it had the most moons in the solar system. But now we've discovered, like, Saturn has more than 80 moons.
Yeah.
So science really does progress. I mean, of course, the addition of a lot of discovery of a lot of moons from the Cassini mission was a huge deal. So Cassini added to that number quite a lot. But yeah, it's quite amazing how much science progresses within a couple of decades.
Actually, I'm glad you brought that up, because it's one of the things I wanted to talk about. First of all, quick side tangent there. You mentioned Cassini and the moon pictures. So this is one of the photos from Cassini. I think it's my favorite space picture of all time. And it is the picture of the moon Mimas floating above the rings of Saturn. So in the foreground here in the bottom, these are Saturn's rings. So the probe is floating above those rings. This is the moon Mimas. The background here, this is Saturn, and the reason why there's this discoloration on Saturn, this is the rings shadow that is falling on Saturn. So there's Saturn's shadow, the rings of the shadow of Saturn's rings falling on Saturn, and Mimas floating above the rings of Saturn. It's such a crazy photo. I love this picture. But you're talking about sort of like what we've known about the planets and how quickly it's changed. I have a photo here I'm going to bring up. So this is an image of Jupiter that was taken by Pioneer 10, and it's something to think about. This photo was taken in 1973. Before 1973, we did not have an up-close photo of the planets yet. We landed on the moon before we got close to Jupiter to take a picture of it. Like, that's not even, that's within just a couple decades. So it's incredible to think how much our view of even just the outer planets in our own solar system has changed just in a couple decades. That before 1973, we had not visited the planets in our own solar system yet. That's astonishing to think. And now we have pictures like the ones that we've seen, even like this. So this was taken by Juno, the latest probe to fly around Jupiter. Check that out. It's incredible.
Wow.
Yeah.
Beautiful.
And one of these as well before moving on to our next target. Look at that. Look at that marbling on Jupiter.
Yeah,
it's astonishing.
That's amazing.
Yeah. Oh. And again, talking about the nature of the fact that it's taken so long for us to explore even our own solar system. One of the last planets that we visited as flying around in probes, and that is Neptune.
Neptune, a very blue planet. Earth is not the only blue planet in our solar system, hey?
No, it's not. Yeah, but for different reasons. So let's see.
For different reasons, yeah. Exactly. Yes.
Now Neptune doesn't show up super detailed in the view from the telescope because it is really, really far away.
It is much farther away and much smaller than Jupiter and Saturn. So
let's see here. Oh, I can barely make it out. I might have to expose a little bit longer.
Yeah. Oh, there we go. There it is. And you can even see it's kind of bluish.
You can. There it is.
Look at that. Look at that. It's even more than a couple pixels. Look at that.
It's a blue dot of Neptune. So, again, we were talking about just how recently we visited planets. We didn't visit Neptune up close with a probe until 1989.
Wow.
Yeah.
It's amazing to think about. So another fact that I have memorized about Neptune is that the pressures on Neptune are so high that it might actually have a diamond core. Yeah. So that's another one of those things. But I think that one is, I'm probably out of date with that particular factoid, but I haven't verified if that's still still a running hypothesis today. But I remember memorizing that.
Yeah, there could even be diamond rain in the clouds of Neptune,
That's
similar
right.
to Jupiter and Saturn. Yeah.
That's right. So basically, just really pressurized carbon raining down on some of these planets is another factoid I heard.
Weird thing about Neptune is Neptune radiates 2.6 times as much energy as it receives from the sun, and we don't really know why that is. Yeah, very strange thing. So all this energy is radiating off of Neptune, and we don't know exactly how it's created, which is kind of
That's interesting. So yes, I think I remember hearing that too. So I suppose one of the only ways you could have that happen is if it's kind of the remnant of a contraction, like that. If Neptune is somehow still contracting, just like when a star starts to form, the gases from a star contract under gravity and gives off a lot of heat from losing all that gravitational energy. It gives it off as heat. And I wonder if maybe, I don't know, I'm just kind of speculating. I'm not a planet scientist at all, so I don't actually know. Maybe, I'm not a specialist in planet science, but I wonder if that might be one of the theories as to why it's giving off energy.
I knew that Neptune was going to be a tiny dot, and so I thought I would supplement it. So this is one of the first pictures that was taken of Neptune by the Voyager 2 spacecraft, which visited the two outer planets, Uranus and Neptune, for the first time. And a really cool thing about them, there's one of these pictures of the atmosphere where there are clouds, high altitude clouds over the other lower altitude atmosphere. So you can actually see shadows being projected by these clouds onto the surface of Neptune. One of the only telescopes that's capable of taking photos of it from this far away is the Hubble Space Telescope, which is why some of the other pictures now, we have pictures almost as clear as this of Neptune now, but of course in present day with the Hubble Space Telescope. Okay, what is next on our list? I think we started with the bright targets first. So Neptune. Oh, we're going to try, I think we're going to try a binary star system.
Oh, good. Okay. So that's the one in Ophiuchus, right?
Mm-hmm.
I don't know if I don't know if I'm pronouncing the name correctly.
I've heard it both ways.
How would you pronounce it?
Ophiuchi? Ophiuchus?
Okay.
Yeah. No. So sometimes the planetarium software has a different name for the catalog star than I might have put in, so I'm going to try to find it.
Yes, that's true. Yeah, there are sometimes different names. But this constellation is, it's quite easy to find if you know where the Big Dipper is. The Big Dipper, the handle, if you follow the handle down to the left of the handle, like follow the handle away from the Big Dipper, then you go down to a star called Arcturus, and that's one of the brightest stars in the constellation of Ophiuchus. So let's take a look.
All right, we got it. Nope, that's not what I wanted to do. All right, waiting for the dome to catch up with the rest of the observatory. Otherwise, we're staring into the ceiling.
Right. Okay. Yeah. So the dome moves a lot slower than the telescope does. The telescope motors are pretty fast, but the dome is a little bit sluggish. But yeah, it eventually does get there.
I think maybe our live view of the telescope has frozen. I don't know why that is.
Oh, really? It sometimes does that.
It's too bad because it's running on my view from here. Oh, there it goes. It's sort of skipping around. It's not
okay.
It's not as fluid as I hoped it would be, but anyways. Okay, we're on target. Let's see what we can see. Hopefully this turns out. If not, I've got a backup plan.
Okay. That's fine. So, a binary star system. So what did you, what was striking about this binary system that What was the reason why it made it onto the list
Made it onto
tonight?
the list tonight.
Yeah.
One of the cool things about it is you can make out both stars in the binary system.
That's cool.
Which is
That's
really
cool.
neat. And, we have a difference between different kinds of binary systems. Some of them are called visual binaries, where they look like two stars close together visually from where we are on Earth, but they may not actually be bound together by gravity, so they're not actually orbiting each other. But this star system is. So these are two stars that are actually in a binary pair. They are held together by gravity, and they are actually orbiting one another. So this system is about 16.6 light years from Earth. Again, it's in the constellation Ophiuchi. It's a poor constellation that gets left out of the zodiac. It actually is one of the zodiac constellations, but we ignore it now. But technically speaking, if you're born between the 29th of November and the 18th of December, you're in Ophiuchus. That's what you are in the zodiac calendar. But it gets left out. Anyway,
the 13th sign.
The 13th sign, of the zodiac. Unfortunately, it's one of the reasons why this constellation gets left out is because of the Earth's axis changes position, right? It wobbles around. And so the sun doesn't end up in the same zodiac constellation since the Babylonians created the zodiac in ancient times, and so we've ignored that one now. But you might technically be an Ophiuchus. Anyways, the primary star in the system is a yellow-orange main sequence star, and so that means it's still burning hydrogen. Any star that's in the main sequence is still burning its primary fuel source, so it's still alive and kicking. It's not evolving toward a later stage of life, and it's orbited by a secondary orange dwarf star. It orbits at about a distance on average of 23.2 astronomical units. And an astronomical unit is the distance of Earth to the sun, so about 150 million kilometers. So to put that in perspective, Neptune is 30 AU, and so it's orbiting within like the same size as our own solar system. You have two stars orbiting each other, which is pretty cool.
Wow, the fact that we can resolve that is pretty amazing. So it must be pretty close. So you said it was 16 light years. Okay, yeah, that's pretty close to us.
So the distance between these stars is like the distance between, like we said, between like Earth or the sun and Neptune, essentially, the distance. But the orbit is highly elliptical. So sometimes it clubs closer toward the distance of Saturn, and then sometimes farther away.
Yeah, so you know that most stars are actually binary star systems. Did you know that?
I did not know that.
Yeah, because binaries are more common than single stars. So I thought that was a very interesting thing to. But just because of the statistics of how stars are born, stars are usually born in groups and clusters. They're right. Born in clusters, and so most of the time the clusters do kind of break apart. But chances are, you'll be born with a star close enough that you'll be gravitationally bound to it.
So what about ours? Because we were born in a cluster then, right? Probably like most other stars. Why is our sun a loner?
We happen to not be in a binary system.
No. Would that affect planet formation? Like, is it better to be in as a lone star for planets?
Yes, it is better to be in a lone star for planets. Yeah, having two stars in your system, unless you're a planet unless you're really far away from the two stars. Being part of a binary system is not good because if you are a planet in such a system, your orbit would be very chaotic and it would not be hospitable to life. But unless you were far away, if the two stars were really close together and you were farther away and somehow still in the habitable zone, then you would be fine.
I remember there being a hypothesis, and I think it's been disproven, is that the sun actually did a very tiny red dwarf star binary pair called Nemesis was the name of the star, and that it might be responsible, its orbit, for like extinction events on our planet, like for kicking objects from like the far edge of our solar system like in, and this is why comet impacts and stuff happen. But I think it's been disproven that that we are not in a gravitationally bound pair with another star. But this was a thing.
Okay,
for a while.
Well, that's good. That's
yes.
good to know.
Yes. Speaking of star clusters, that's what's next on our list. They're one of my favorite targets is star clusters. So this target is called Messier 56, and it is a globular star cluster. And,
yay!
They are quite dramatic. So rather than 1 point of light or two, like we've been looking at, we're going to get a lot more. So here we go.
Oh, good. Globular clusters are fun because they're, like if you imagine the Milky Way as like a disc, right, with spiral arms, like a plate, the globular clusters are distributed kind of in a sphere around this plate. And so it's just kind of a fun thing. They're part of what's called the stellar halo. So there is a halo around our Milky Way galaxy that's made of stars, and globular clusters also inhabit this halo. And so this is one of them. So globular clusters are really fun because we're not really quite sure how they formed. It's kind of a mystery. If any of you out there are looking for a career and are wanting to solve some mysteries in science and astronomy, well, here's a problem. How do globular clusters form? It's kind of a mystery. There are a bunch of reasons why it's a hard problem. It's because they're really dense. How do you form something that dense and something so massive out of a single cloud? And how come they haven't broken up yet? And why are they in a halo instead of in the disk of the Milky Way? Things like that. Why are they so old is another thing. So,
yeah, some of the stars in this cluster have been dated at 13.7 billion years. So that's like almost the age of the entire universe. All right.
Yeah. All right. Let's take a look at this.
Now, for those of you just joining us, if you've never been in one of our Starry Nights before, I've switched camera modes. So because we're looking at a far more distant, faint object rather than one singular bright point, we do something instead called stacking. So what happens is we layer individual images. Each one of them are a 20-second exposure, and we sandwich them all on top of each other. And basically, it's a way of adding more light together over time for a distant fader object to make it more resolved and brighter. So we've taken now 4 stacks, so there's a total exposure of 80 seconds. You can see it here on the screen. And now, because we have a little bit more data, I can try to boost some of the brightness on the image so that we're able to see the stars more clearly.
So there's a comment here in the chat. Somebody asks if stated that or asked that are globular clusters wannabe galaxies, and that's a great question because globular clusters, some of them, the most massive ones, are about the same mass or even more massive than some of the smallest dwarf galaxies. But there is a real difference between dwarf galaxies and globular clusters. So there are a bunch of dwarf galaxies that are orbiting the Milky Way. And of course, there are the globular clusters. But there is a difference between them because what the biggest difference, and somebody just asked here, aren't they packed with dark matter? Globular clusters don't have dark matter, but dwarf galaxies do. We can tell that from the orbits of the stars. So the orbits of the stars in globular clusters are such, they just look like they're, there's not very much dark matter. There's no dark matter in them, basically. And whereas dwarf galaxies have quite a lot of dark matter. They're completely dominated by dark matter. The stars that you see in a dwarf galaxy are like this tiny fraction of the entire mass of the whole thing. And you can see that in the orbits of the stars. So yeah, there is actually a difference between them. So their formation mechanisms must be also different as well.
That's so cool.
Great questions we have here in the chat.
Yeah. This particular globular cluster is in a retrograde orbit around the Milky Way. So it's orbiting kind of the reverse direction of other globular clusters.
Cool.
And so the theory is that maybe then it was picked up by a merger with another galaxy, because other galaxies also have globular clusters. And so this one may have been donated by a merger with another galaxy. There is the largest of the globular clusters in the galaxies is unfortunately we can't see from the northern hemisphere. It's in the southern hemisphere called Omega Centauri. And there is a theory that maybe Omega Centauri as a cluster, because it is so huge, might be the leftover center of another dwarf galaxy that it might have merged with the Milky Way at some point in the past. But we're not exactly sure. So these are some of these mysteries of globular clusters. Cool thing that I read about recently, I wrote an article on this actually, and there are some people speculating that about the existence of advanced civilizations in globular clusters. Now, as we just noted previously, having a lot of stars close by to you might disrupt formation of planets in your solar system. But if we forego that for a moment, if we say, hey, someone might be able to live inside of a globular cluster, they would have some huge advantages to spread out, because the travel time between stars would be so short because they're so close together. Communication time between the stars would be really short. It would be on order of maybe weeks or months instead of like years like it is in the disk of the Milky Way. So there'd be some huge advantages to be able to settle in a globular cluster if you could. And the people that had written the research that I was writing about suggested that maybe we should be beaming more signals to globular clusters, or listening to see if there are any signals coming from globular clusters. So there you go.
So somebody here asked a question in the chat of how do we know the orbits of stars? And that's also a great question. So I was saying that we could tell the presence of dark matter with using the orbits. And the way that we can measure it is we don't watch the orbits of the stars. They take way far too long for us to watch. But what we do is we use the Doppler effect. So just like you would, like the police, are checking with radar to see how fast you're going. We do basically the same thing with stars. We look at their light signatures and we measure redshift and blue shift in the stars, and that's how we know how fast they're going. So we can only see it, their velocities toward us or away from us. So we can't measure horizontal motion, but we can measure motion toward us or away from us. And when you do that for lots of the stars and you average them, then you can that's how you get the orbit of the stars around the center.
Very cool. I think this turned out really well. We got a lot of stars in
Yeah.
this picture. This is really neat. So
Yes.
yeah, a cool thing. There's a very neat story by Isaac Asimov that is written. It takes place inside of a globular cluster. It's called Nightfall, and I think this is a common piece of info that we bring up on a regular basis about globular clusters. But it's possible that if you did live on a planet orbiting a star within a cluster like this, there'd be so many stars so close to you that you wouldn't really experience a nighttime. Like your sky would be so bright with so many other globes of light around you that your view of the universe would be quite different. You may not even know that there is a galaxy out there that you're a part of. Who knows? Imagine how science would be impacted, Joanna, if we never could see the sky.
Yeah, that would be pretty crazy if you could never see the Milky Way. Could you imagine that? Like,
Yeah.
if your sky is just dominated by all these bright stars? Yeah.
So much-
I think that you could see it would be nighttime, but the stars would be it would be a bright nighttime. You could get, if you were orbiting a star, you'd get a pretty bright nighttime, especially if you were kind of near the outer edge of the globular cluster.
Right.
If you were on the very edge, that would be actually kind of cool, because on one side you'd see this massive, one side of the sky, it would be like bright stars. On the other side, you would see kind of the rest of the Milky Way. That would be kind of, if you were right on the edge. Can you imagine that?
That would be a wild, wild sky. Wow. Imagine. That would be really neat. All right. Okay, moving on. What else we got here on our list? I think we're going to try now that it's darker. So on our list of things, we had some other faint. This is where we start getting into the fainter nebulous objects. So we're going to try
But it's
something.
a beautiful sky tonight. I think we're gonna be able to see some of these faint objects.
I think so too, and the advantage is that we don't have a moon. So in other nights that we had clear skies, we had a moon in the sky, and the moon is a very jealous object. It all of its light and glow tends to obscure some of these fainter, distant objects that we want to check out. So this is a nebula called the Crescent Nebula. I don't know if this one's going to show up. So this is a bit of an experiment because this nebula shows more in wavelengths that we're not imaging in right now with the telescope. But let's see what happens. We're going to try it. I have a backup photo in case it doesn't work.
Okay. Yeah, this one will be a faint one. The main camera that we use does pick it up, but this color camera, it was cloudy all week, so we didn't have a chance to try it out ahead of time. But I am curious to see if it'll work in this camera.
Yeah, that is a good point. We normally have, I'm catching the motion now. We try to double check our targets before we put them out for a starry night. And we weren't able to do that this week because we didn't have any clear sky until like today. So
Exactly. This is one of the rare nights in the entire season that we actually get clear skies. Yeah, so the Crescent Nebula. So what is the Crescent Nebula? So why did the Crescent Nebula make the list today?
So the Crescent Nebula is cool because it's not really a lot of the nebula that we look at, especially planetary nebula that we look at, are created by the death of a star. This nebula is created more kind of a star that is going through an evolutionary stage where it's heading into a red giant, but it's such a massive star that it's basically just blowing outer layers of itself off into space. And those outer layers are, with these big expulsions, are colliding into material that the star had previously ejected. So there's basically like a demolition derby of stuff flying off of this star. Now, again, I don't know if we're going to pick it up because it glows primarily in a type of light called hydrogen alpha. So it's a light that's given off by excited hydrogen, and typically you have to see that light with certain filters. And our main telescope has filters like that, but our main telescope's camera, this is kind of our streaming camera, and it does see mainly in red, green, and blue light that your eye sees. So we're in optical wavelengths. So this nebula is not always super visible in optical wavelengths, but I put it on here anyway just to see if it would turn out. So we'll see what happens.
Okay. Oh, you can see some of it. Oh, cool.
You can look at it here. You can actually see the haze of it, the outer edge here.
Oh, there we go.
That is pretty neat. And down here you can see I'm often adjusting color. So we have this curve, this histogram curve that comes off of the image that shows us light that's coming off of the object. It's also a mix too of just some of the sky glow that we have. Our telescope is at Simon Fraser University and Burnaby Mountain. So it's not right downtown or in Vancouver, but it is pretty close to the city that you still get some glow from the sky. And so what I'm trying to do is align the colors. You can see we have like an extra bit of green, and that can hide some of the wispy clouds from a nebula. And so we're going to try to balance the colors out a little bit more to give more of a neutral looking sky.
Yeah, so what that histogram is, it just tells you how many pixels are of a particular brightness. So, so he's just kind of moving the limits around so that we can block out all the pixel values that are less than this level of brightness and block out ones that are brighter than this level. So that's what he's doing right there. Now, and that enhances the image. So now you can see some of the wispy hydrogen
yeah, you can see it here.
Clouds here. Yeah, that's pretty cool.
Yeah, so this is the outer material being blown off of a massive star 5,000 light years away. And what's happening is that the star had evolved into a red giant, we think probably about 250,000 years ago. And then what's happening is it's basically, because it is such a massive star, it's about 15 times the mass of our sun. It's letting off these huge bursts of energy and material. And that material is hitting, this faster material is hitting these outer layers that it had already expelled in the past, and it's hitting them and kind of creating this shock wave. So what you're seeing, the denser part here on the outside where I'm tracing my mouse, is kind of the shock wave of that material. I'm surprised it showed up at all. I didn't think we'd actually be able to see anything. So that is
Yeah.
pretty cool.
Yeah, we can see some of it. So that's pretty cool. So you'll see a lot of pictures of emission nebulae, like the famous Orion Nebula, or the Lagoon Nebula, or a lot of the ones that are sites of star formation. They usually glow quite strongly in pink or red, and you can see that here in our camera. It's quite red. So I mean, we are adjusting the colors so that the background sky looks more black rather than green or blue. Yep. So that's what Matthew's doing here, is adjusting it so that the sky looks black. But you can see that the part of the nebula glows red or pink, like pinkish red kind of thing. And that is a signature of which element? Who knows that? I know I've talked about this before on Starry Nights, but what does pinkish red mean in nebulae? I know there's a bit of a delay between our talking and it getting through to YouTube, so we'll have to wait a couple seconds to see if anybody knows the answer. Hydrogen! Somebody got the answer! Yay! Yes, pinkish red in pictures like this means hydrogen, and that's because one of the most because hydrogen has an electron, a single electron, right? It's an electron orbiting a proton, and around when hydrogen gets injected with energy, that electron gets bumped up to an orbital that has a higher energy, and then it comes back down again, down to its lowest energy state. And when it does that, it emits a photon of a very, very precise wavelength. And wavelength for light means color. And that very precise wavelength is this reddish pink. So that's why hydrogen is the most abundant element in the universe. So you'll see nebulae are full of hydrogen. So you'll see pink in a lot of these pictures.
This is awesome. A couple questions there. One, will this star go supernova one day? Yes, it eventually will explode. It's massive enough to become a supernova. And Probably within, I would say, a few hundred. Someone already found it. Yeah, 100,000 years. So yes. So yeah, and when stars are massive enough, they have to be bigger than our sun. They produce a lot of iron in their core, and iron is what will trigger a supernova, the sudden collapse of the star in on itself, and then a rebound out into space. As far as which star it's coming from, I don't actually think we're centered on the central star in this image, because our telescope view of this is only looking at a part of the nebula. It kind of looks like a brain, and that's why I was glad that I saved an actual photo of it. If we could do a longer exposure of it, it would look... Oh, maybe I didn't have it here. Oh, let's bring it up here.
We actually have done a longer exposure of this nebula, but we haven't processed it yet. But one of these days we should do that, because it's a very pretty one, and it's huge. It's much bigger than the field of view of this camera.
Yeah, so we're looking kind of at only at one corner, but it looks like this kind of brain out in space, which is really neat.
Yeah.
Yeah. There you go. Okay. Shall we move on?
Sure.
All right. I think next on the list was the Veil Nebula.
Oh, yay. That one's a supernova remnant.
Yeah, so someone had asked about supernovas. Well, this is part of one of those, so here we go.
Yes. It's a supernova remnant, and it's pretty cool because it exploded quite a long time ago. I think it's on the order of 100,000 years or so ago. So a long time by our estimation, but like yesterday in astronomical terms. But yes, the Veil Nebula was quite a violent explosion. And what's cool about it is that we've never been able to find the neutrons, like most supernovae result in neutron stars. Some of them result in black holes, but we haven't been able to find the neutron star that resulted from this. So it may have resulted in a black hole. But the other thing, though, is that since doesn't seem to be evidence of a remnant, it may also have been the supernova might have been a special type where two neutron stars collide, and produces a special type of supernova. So this might actually be the remnant of a particular special type of supernova that we use to measure distances to other galaxies. All right.
Earlier in the year, we were doing a lot brighter nebulas. They were mainly star-forming nebulas, stellar nurseries. Right now, we're actually looking instead of nebulas created by the deaths of stars. But we're kind of at a time of the year where a lot of those star-forming regions, which are more toward the center of the galaxy, are actually not visible right now. And so we're going to have one later on toward the winter, which is the Orion Nebula, one of the closer star-forming regions to Earth. But so since our last time doing Starry Nights, we had like the Lagoon Nebula and the Eagle Nebula, these very bright nebula that are filled with many, many stars. But right now, those aren't as visible, so we're doing these kind of fainter death of star nebulas rather than birth of star nebulas. All right, so there we go. Starting to stack the veil.
Okay, let's take a look. I know we've done this one successfully before, so I'm excited to see it. Right, so this supernova remnant is in the constellation of Cygnus the Swan, and so that's normally a summer constellation, but you can still see it now. It's still pretty high in the sky, and it's Cygnus the Swan is also known as the Northern Cross. It's like a big kind of a cross in the sky, and it's lined up almost precisely along the band of the Milky Way. So if you're out camping and you see the Milky Way overhead, it's very likely going through the constellation of Cygnus. And so actually most supernova remnants and nebulae are found along the Milky Way, along the glow of the Milky Way, because that's where most of the stars and star-forming regions are in the sky, in the galaxy.
Yeah, it's amazing that some supernova remnants, they can get so big that they actually get lost in the galaxy. And you might think, well, how can that be? How can something so big get lost? And it's because the gases expand outward so fast and the structure grows so quickly that it starts looking like the other larger gaseous structures of the galaxy. So they actually become almost invisible. They sort of fade into the background. The Cygnus Loop, which is a kind of a big structure that's made of several of these nebula, is all kind of part of either one large supernova or a series of supernovas sort of in this direction of the sky. All right, let's see what we've got. We've got 6 stacks now, so See if we can bring anything up.
All right. So somebody was asking about the James Webb telescope. So hopefully it'll be launched very soon. That was the promise.
December the 18th. Supposed to be. There it goes.
So cross fingers. Hopefully that will be launched soon. So the James Webb will be amazing. It will be fantastic. It is focused on the infrared though, so it won't be optical images, but it's focused on the infrared so that we can see very, very distant galaxies. At least that's the type of science that I'm more familiar with. But the galaxies that are extremely far away have experienced what's called a redshift. Their light has been reddened because of the expansion of the universe and because of redshift. Actually, it's like because the expansion of the universe makes them look like they're moving really fast away from us, and so their light, what we would normally consider the visible wavelengths if we were at the galaxy, has moved into the infrared. So the James Webb has I believe only infrared instruments. The other thing that the James Webb was meant to study is also locally in our own galaxy. Was meant to look at the birth of stars and planets in our own galaxy, which you can only really study also in the infrared because the dust that surrounds young stars blocks all the visible light. So yes, the instruments on the James Webb will be in the infrared. So the images will be different. It won't be the optical, like it won't be kind of what we normally associate with astronomy pictures.
I'm retargeting just because the part of the veil that I was focused on, I remember having issues because there's one really, really bright star in the center that kind of overexposes everything. So I'm moving from this part, which is the eastern veil, to this part over here, which is the western veil. So that's what we're doing.
Oh, right.
I think it'll show up a little bit better.
Okay. Good. Let's try that.
Yeah, while we're doing this, so the James Webb Space Telescope, we'll just chat about that quickly because it's very exciting because people ask, well, how would it compare to what we're seeing? Well, the James Webb Space Telescope is going to be about 100 times more powerful than even the Hubble Space Telescope is. One of the missions of that telescope is something called First Light. So remember, when you're looking back through space, you're also looking back through time. One of the missions of the telescope is to take pictures of the first stars that were ever born in the entire universe. So when those images start getting resolved, we'll be the first human beings to ever see the first stars. This kind of link across all of space and time, which is pretty astonishing. Right now,
yes,
its route through the water is secret, Joanna. I don't know if you knew this or not. And they've sent decoy boats out that all look the same to try to fight off piracy.
Wow, really?
Yeah.
Wow. All right, let's see what we can see here.
All right.
Hey, there it is.
There it is.
Wow. Hey, and notice what color it is. It's pink, pinkish red, which tells you that it's made of hydrogen.
Oh, that's a little
Wow, great. Yeah, this is a very faint target, so it's quite hard to see in smaller telescopes. If you have a smaller backyard telescope, this will be very, very difficult to see. So it's our telescope's 70 centimeters in diameter. The most important property of a telescope is the size of its, like the primary mirror or the primary lens. So if you have a telescope that has a lens, then the one in the front, the size of it is the most important property of a telescope. So if you're out for looking for a telescope, bigger is always better. So, because it's the amount of light that you can collect at once that determines how bright your image is. So, this object is very faint and very hard. So, you can see that the sky, you can see the sky noise around it. The sky is very bright, especially here in Vancouver. The sky glows at a certain brightness, and the objects that you can see depend a little bit on the contrast between the object and the sky. So the difference in brightness, and it's quite it's quite faint. So if you go out to darker skies, it's easier to see, but even still, it would be hard to see it without a camera. A camera can expose and collect a lot more light at once. So we're exposing for 20 seconds here, and that's why you can actually see anything at all.
Yeah, so the wispy haze of a destroyed star.
That's right.
Oh, that's no good. I believe I may have lost my connection to the observatory.
Oh, really? Okay, here, let me try to see if I can do anything here. Let's see. Ooh.
Are you connected?
I am connected.
Okay, but the stream is gone now. Okay, let me try to reopen.
Oh, the stream is gone?
Yeah, because I've lost my stream window. Okay, everyone give me 1 second, and I'm gonna try to.
But you're still connected to the stream.
I'm connected to the stream. It's just that my
okay.
My connection to the observatory crashed. The JavaScript app.
All right. Oh, okay, that's all right.
Everyone give me 1 second.
Oh God, I can adjust the image a little bit. Let's see.
All right, let me.
Yeah, isn't that pretty?
Well, I'm glad you can see it. Nobody else can right now.
What, nobody else can see it? No, I thought you said the stream. Oh, the app. Okay, so the app crashed, and so now you. Oh, I see. Okay, yep. So you're not streaming the app anymore.
Someone give me 1 moment. I will try to get it back.
No problem. So, the Veil Nebula. Yes, it's a supernova remnant. Supernovae are huge explosions. So, actually, I even just talked about this in my physics class today. How do supernovae happen, and why are they what causes the explosion? So if you ever bounced a tennis ball on the ground, right, you just drop it from whatever height, it doesn't go very far. It doesn't bounce back very far. It does bounce back, but it doesn't bounce very far. But if you ever tried the trick where you take a basketball and then you put the tennis ball on top of it and then you drop them both together, do you know what happens? Have you ever seen this? The tennis ball just shoots up like nobody's business. It goes up really fast. So what happens is, because the basketball hits the ground and then it transfers its momentum to the tennis ball, and the tennis ball shoots up really, really quickly. And that's exactly what a supernova is. So what's happening with a supernova? The inside of the star, the core, collapses very quickly. From within a split second, a bit of the core of the star collapses into this tiny little, something the size of the sun collapses into something the size of a city, and in a split second. And then there's empty space in that, what's left over, right? But the upper layers of the star, because the star is much, much bigger than the sun, but the upper layers of the star have to fall down onto this neutron star. So the lower layers are like the basketball, and the upper layers are like the tennis ball, and the layers just explode because just for the same reason that the tennis ball shoots up when you've bounced it with the basketball. It's the same reason why we have an explosion, because the outer layers are like the tennis ball, and they explode out into space kind of a billion times more than your basketball and tennis ball analogy.
Okay, I think we're back.
We're back. Beautiful.
All right.
Okay.
And that veil looks really nice, because as we've been sitting here, it got exposed for another 3 minutes. So
yeah, exactly.
A lot of clarity there. Sorry about that, everyone. I've never had that app crash on me before. I'm glad that you can actually repair it during the stream live. I didn't know that we could even do that.
Yeah. Well, in any case, right.
All right.
Well, now we're back. We're seeing a beautiful Veil Nebula.
Okay, and now it's time to move into your area of expertise. So you mentioned earlier you're not a planetary scientist or geologist. So Dr. Joanna Wu, what is your area of expertise?
So I study galaxies, and you heard a little bit from Kelvin earlier today, and how he was doing this project on this how star formation stops in galaxies. So he was working with me this summer, and he did a great job on this project, analyzing the simulations of galaxies and trying to understand how they stop forming stars, and if that quenching, it's called quenching as he explained, how that quenching is related to the density of galaxies. So I thought he did a great job explaining what he did. So he basically explained everything. I don't really have anything else to say. But we could take a look at some galaxies, and maybe I could tell you a little bit about these particular galaxies.
All right, so let's try. I'm going to try the Fireworks Galaxy, I think.
The Fireworks Galaxy. Okay, I don't think I've seen that one.
Galaxy imaging is notoriously finicky from here, so let's see what happens.
Oh, right, the Fireworks Galaxy. So I'm not familiar with this one. Is this one a spiral galaxy?
It is, yeah. It's a face-on spiral galaxy, so it's very exciting because it's really super clear. And again, it has, so that's kind of its like nickname. So the observatory doesn't know what it's called, so I have to give it its fancy sciencey name, which is NGC 6946. So that's what we're going to do. Actually, of course. Since you're here, Joanna, so you know what these things mean. Like, so when we are typing all these like strange numbers and acronyms in, what does something like NGC mean?
So NGC means the New General Catalog, which is no longer new. It's very old, actually. But it stands for the New General Catalog because so astronomy has been a science for hundreds of years, and since forever, people have started creating catalogs of things. So first, because before we had really good telescopes, people made catalogs of the stars, and of course there were thousands, tens of thousands of objects in these catalogs. And then somebody decided to create a catalog of like stars and nebulae, and before they knew nebulae were galaxies. So Hubble was the one who discovered what galaxies were. But before that, they decided to have so there was a catalog of nebulae, and Messier created a catalog of nebulae, and then there were catalogs of stars. And then somebody wanted to create a more of a general catalog. It actually doesn't include stars, but it's a more of a general catalog of a whole bunch of different types of nebulae. So they were called nebulae at the time, but now we know that they are actually galaxies. So there was actually a debate in the 1920s as to whether or not these spiral they look like little clouds of fuzz, right? And so there was a debate about whether or not they were actually within our own Milky Way, that they were close by, or if they were themselves like what they were called island universes that were outside of our Milky Way. And there was a big debate about that, and there were lots of interesting arguments. And then Hubble measured the distance to what was called then the Andromeda Nebula, which I think we're going to see tonight, aren't we? Do we have time?
Yeah, I think so, because I don't know if Fireworks is going to work out. So one of the ways that the what's happening here is when we talked earlier about stacks, so how the image is layered on top of one another. The images have to be aligned with each other because the sky is moving as the telescope is imaging, and so all the layers need to line up, and the way that alignment is done is with stars. Now, here's a problem with imaging galaxies. When we're imaging galaxies, we're looking always outside of the Milky Way, and so usually to areas of the sky that are not as densely populated with stars. And that unfortunately means that sometimes the computer has a hard time locking onto the target because there aren't enough reference stars to line the images anymore. And so that's what's happening here, is that we're not getting enough stars in this part of the sky to align the image. I'm going to see if we can stretch it anyway, because this galaxy is very pretty. Oh, we're still moving.
Oh, oops. The first image was still
motion, so maybe that had something to do with it.
Motion.
We'll try again.
Okay,
I saw
we'll
part
try
of it
again.
in there. But if not, we'll try another galaxy.
Okay. Well, in any case, so So now we know that galaxies are themselves very, very far away. Our own galaxy has something like 100 billion stars, and there are at least that many galaxies in the universe. Actually, more. I had that number, but I don't have it memorized. But anyways, what's the difference, right? Because we can't, our minds just can't comprehend such numbers, right? Like it's just, so there are that many galaxies, and each of those galaxies has something like 100 billion stars, and it's just really, really mind blowing. And there's just vast amounts of empty space between each galaxy. It's really quite mind blowing. So how are we doing here for
the first frame, or the first two frames actually stacked, so we may
Oh,
we may have acquired the target. And 3 stacks, hooray!
Okay, so it looks like we're in business.
We're in business, so let's see what we've got in there. It's like opening a space present every time we start stretching an image.
That's a great analogy.
Yeah. What has space left for us today?
Yes, under the tree. Hey, I do see the galaxy.
Oh, there it is. That's the core. There are the spiral arms.
Okay, so let's
this will only start getting better. There's a lot of green cast here, so let's get some of the green down.
So spiral galaxies. So when you heard about Kelvin's project of the density of galaxies and how density is related to the quenching of star formation, it's because it's indirectly related to the black hole. But so spiral galaxies are quite dense in the centers, and then the density of stars decreases exponentially as you go outward from the center. So that's why the brightness as well. The brightness is correlated with the density. So the brightness decreases exponentially. So that's why you can see the centers quite brightly, but you can't really see the spiral arms that well. But you can almost see them. They're starting to come. As we stack, we'll start seeing more detail in the spiral arms.
Yeah, I can see them here.
But, right,
yeah.
Yes. Yeah, you can sort of see them still, yeah.
I'll zoom in a little bit more on it. Oh,
but elliptical galaxies. So elliptical galaxies are far denser than spiral galaxies, and the decrease in brightness from the center to the outsides is faster than exponential. So if you thought exponentially decreasing was fast, elliptical galaxies decrease their brightness even faster than that. So they're very, very concentrated. So most of their mass and their light is concentrated in the centers. Whereas spiral galaxies they're kind of more fluffy. They're not as dense. And there you go. There's that galaxy.
It's
beautiful.
In there. Yeah, you can see the spiral out from it, so that's cool.
Yeah.
It's not as bright as I'd hoped, but it is there.
Yeah, it's there. And you can see the spiral arms. Yeah. So again, it's, the quality of your image does depend a lot on the contrast between the actual object and the sky brightness. So we're seeing a lot of noise from the sky, but as we stack, we'll probably see a little bit more detail, we only have 15 minutes left, so maybe
we could move on to a brighter galaxy. Would you recommend Andromeda? We could do that one if you wanted to.
Or what else did you have planned?
We had on the list, what else do we have here? We had the fireworks, we had M81 and M82.
M81 and M82 are beautiful, so maybe M82?
Mm-hmm.
M82 is a great one. It's that one's a fun one because it's got these outflows which you can actually see.
Yeah, this is
the fireworks galaxy is pretty cool too. That's pretty nice actually.
Yeah, I'm starting to see more of the structure there, which is pretty cool.
Yeah.
All right, let's switch to M82. And this is like the opposite of a quenched galaxy, or quenched.
Quenched. We say quite. I mean, it's yes. Astronomers are not known for our creativity and names. So, so we say quenching. And I know a lot of my colleagues really hate the word, but it's stuck. We call it quenching, the quenching of star formation. This galaxy that we're about to see, it's also known as the Cigar Galaxy because it's kind of shaped. We're seeing it kind of from the side, so it looks a little bit elongated, but it's interacting with its neighbor, M81, and that interaction is causing a huge starburst in the center of this galaxy. So what happens is that the gravitational interactions caused all the all the gas in the galaxy to just flow towards the center of the galaxy. And when you have lots of gas in one area, you start creating tons of stars. And that's called a starburst. When the galaxy forms stars at a very fast rate, it's called a starburst. And that starburst, lots of stars, means you have, like our star has a solar wind. if you have lots and lots of young stars have an even stronger solar wind. And if you have lots of them together, you get this really strong wind from the stars that just funnel out into these two outflows. And you can actually see them in our telescope, which is, you can see a little kind of little bits of them. So let's see if it works. Oh, where are we right now? Let's see. Oh, MED2 is a little bit, that is a little bit
low.
Low.
It might be
and
in
it's
some of the campus lights.
And in fact, it's low and it's right in the north, so we might be pointed right at a building. So, okay, so maybe not MED2.
I found there was one star in there, but I think we have so much other glow, like random glow, that I don't think we're going to make out the galaxy, unfortunately. We could try MED1.
MED1 is right next to it, so I doubt if we can't see MED2, I doubt we'll be able to see MED1.
What about...
So how about Andromeda then?
Okay.
Andromeda is always a good... Andromeda is nice and bright. Actually, Andromeda is really easy to see with your, I mean, it's not easy, but you can see it with your naked eyes. It's actually pretty bright. And it was so amazing the first time I identified it. You have to star hop a little bit from Pegasus. So you can see that square on the right. That's the square of Pegasus, the square of stars. That's the square of Pegasus. And you kind of have to star hop from the square to find Andromeda. The Andromeda is pointed out in the red bullseye there, but you star hop a little bit to find it. And it's easiest first to use a pair of binoculars, but once you've found it, it's like this fuzz. Take off your binoculars and look at it with your eyes. And it's really amazing because it's the Andromeda Galaxy is the farthest object that we can see with the naked eye. It's something like 2 million light years away. And so photons flying from Andromeda took 2 million years to fly from there into our eyeballs. It's kind of just this trippy thing to think about. It's like, whoa, you're seeing this galaxy. And you can see it, but it's hard, you can't really see it from the city. You do have to kind of get out of the city in order to see it, but but when you do see it, it's pretty cool.
Another way to try to find it, if you're looking here, I've got the W of Cassiopeia. The second W, if you see just the second half of it, almost points directly to Andromeda like an arrow. So if you follow as well the point from Cassiopeia, you see that fuzzy blob in the sky, you're looking at Andromeda.
Yeah. Oh, I haven't heard that method. Yeah, I usually star hop from Pegasus.
Yeah, I can do it. Somewhere between the two, you'll find it right there.
Yes. Yeah, you have to. I remember staring at the star maps forever to try to to try to identify which star. Okay, that's that star, and then wow, there it is.
There it is.
Yeah. Hey! Yay!
Well, I can see a bright core right on the first exposure, so that's good. I'm wondering again if we have enough stars to lock this one. So let's see what happens.
So usually it's pretty good.
It did. It stacked.
Yeah, it did. It stacked. Wonderful.
Hooray.
Right. So the Andromeda Galaxy, again, the core right in the center, it's the densest part. And then this is a spiral galaxy. So it'll decrease exponentially in brightness as you go away from the galaxy. So the Andromeda Galaxy is huge because it's so close to us. I know 2 million light years doesn't seem close, but like on the scale of the universe, it's pretty close to us. And so it's way, way bigger than the scale of this camera. We are only seeing really the very center of the galaxy in this image. And in fact, the entire scale of the Andromeda Galaxy is something like 3 degrees, which means like 6 full moons linked side by side is basically the size of the Andromeda Galaxy. But of course, you can't see the whole thing with your eyes. Really, with your naked eye, you can only see really the core of it. But it's cool when you do see it. Hey, there it is. And what's cool about this is that you can actually see some of the dust lanes in this galaxy blocking kind of the. You can already see, in the left, right there.
Even here.
So you can see a little bit on that side too, but most of the dust is on the left side. And so that's how we kind of know which way it's facing us. So the left side of this image is the side of the galaxy that's closer to us. And because the dust blocks light from the inner part of the galaxy. Whereas the other side, if you can't really see the dust, that means that the light we're seeing, that's the far side of the galaxy.
You can see the dust lanes here. And so these are not artifacts in the camera. This is actually the dust blocking some of the light from that distant galaxy.
Yep, that's right. That's right. All right.
Cool thing about Andromeda, so as you mentioned, it was like the galaxy that opened up our view of the universe, because we thought the whole Milky Way was, the entire universe until like 1926. So we actually, at the Andromeda Galaxy, have been replicating at the Trottier Observatory, we replicated that distance calculation to the Andromeda Galaxy using variable stars, the stars that change in luminosity over a period of time. We can use them as something called a standard candle in space. And so that research was actually done by an astronomer named Henrietta Swan-Leavitt. It's called Leavitt's Law. These measurements to these variable stars, and that data, that research that was done by Henrietta Swan-Leavitt was then used by Hubble to make that calculation, and we did it too. And I think we did it way accurately than Hubble did. Hubble got like 900,000 light years, which was it was enough to know that it was outside of the Milky Way. I think we got 2.3 million. The understood was 2.4, so we got pretty close even with our own telescope, which was cool.
Yeah, that was a very impressive project. You guys did that before I joined SFU, and I was just so impressed when I heard that project to replicate that distance measurement. It was really impressive. So Cepheid Variables, as Matthew was saying, is are stars that pulsate, and they get brighter and dimmer in a very specific pattern that correlates with their intrinsic brightness. So if you measure the pulsation, then you know what their intrinsic brightness is, and then you compare that to what you actually see their brightness is, and you know that the farther away something is, the dimmer it looks. So if you know how bright it looks, and you know how bright it really is, then you can infer the distance. And so that's how Hubble first at least attempted to measure the distance to Andromeda, and discovered that it was outside our galaxy. And that's how you and other people at the Trottier Observatory measured the distance to the Andromeda Galaxy.
I think it's the only scientific paper I have a name on, so that's pretty cool. I don't know if I actually have the picture that I did of Andromeda somewhere or not.
It must be in the gallery somewhere.
It must be in there, because one of them, the reason why I wanted to point it out is that the variable star that was used, that Hubble used primarily to lock the other variables, is somewhere in the photo. I captured it. I didn't know it was in the view of Andromeda that I'd selected. It was Howard Trottier who noted it was in there, and I have a little circle in it somewhere, but I don't know where I put it. I don't know if I have it on there or not. That's okay.
That's all right.
But yeah, it's the final picture ended up turning out pretty good.
Yeah.
I just don't know if I have it anywhere. That's okay.
Yeah, there it is.
Do we want to try another galaxy?
Well, we have 3 minutes left. Did you have another galaxy in mind that we should try?
We could try Whirlpool, I guess.
The Whirlpool will be very difficult. That will, but we could try it.
Actually, I found that photo is online. Here, 1 second.
Oh, okay. Let's take a look then.
There it is.
And there it is. Beautiful.
So that's the picture there. So this is that's the core and spiral arms of Andromeda, and they're highlighted in this square. That is the variable star. It's called M31V1, and was one of the Cepheid variables that tipped us off that Andromeda might be way farther away and therefore outside of our galaxy. So to give you an idea of how much exposure time, this is 5.5 hours of exposure time in order to get an image like this in our primary camera. So when we're doing the live stream, of course, we can only expose an object for a few minutes. But if you're wondering how that much detail comes out in space photos, that's why, because we'll be centered on one target for hours and hours and hours in order to get that much detail out of the image. And
Yes,
so
exactly.
these dust lanes here that you can see there that are more resolved in the photo after all that exposure time, but that's what you're seeing here in this image through the web camera that we have attached to the periscope on the telescope. So those are the same dust lanes orbiting around the center of the galaxy.
Yeah, and also you use the main camera, which is a lot more sensitive. So the same image, like if you expose for a few minutes on the main camera versus a few minutes on this camera, there's a huge difference because the main camera is more sensitive. But the downside of the main camera is that it's black and white, and so you have to expose it with different filters and like a red and a green and a blue filter in order to and then combine them later to make a color image. The advantage of this camera that we're using now is that you can get the color image right away.
Yes. Yeah. Okay, so we're basically at time, but I had one thing I wanted to see the reason why I left it to the very end is that right at 10 o'clock, it just makes it over the edge of the observatory's viewable area, I think. So let's
see. All right, let's see. What were you thinking of?
It's a star called Fomalhaut, and it's known as the Lonely Autumn Star. And so since we're in autumn now, I figured we would pick that target and see if we can actually target it. It might be a little bit too low for the dome. So the dome of our telescope has a shutter that drops out, and that means that about 10 degrees of the sky, if anything's lower than 10 degrees on the horizon, it kind of gets cut off. And this star hit 10 degrees right at 10 p.m. today. So it's going to be really close to the margin, but we'll see whether or not it shows up.
Okay, exciting. Let's see.
Oh, I don't think did the telescope even move? It may not have. No, it's outside of the altitude limits.
Oh, too bad.
It was so close. Okay. Anyways, we'll have to do it next time, I guess, on that one. It's known as the Lonely Autumn Star because it's one of the brightest stars in the sky that's not neighbored by any other bright stars at all. So, and there are archaeological digs that show that it's been used in kind of seasonal change ceremonies dating all the way back to like 2500 BC, which is pretty cool. And it's also the first star that ever had a planet directly imaged around it by the Hubble Space Telescope. But we'll have to save that for next time. But happy autumn, everyone.
So those of you who were wanting to know where it is, it's right here. It's near the south here, and it's quite low in the sky. There it is. So
yeah, it's because it's too low that it's set outside the boundaries of where the telescope will go. So we can't make that. I was going to make that our big grand outro, but we'll have to wait another time. I'm just glad we had a clear sky.
Another time then. Yes, beautiful clear skies tonight. Thank you all for joining. This was so fun.
Yeah, and again, remember, we'll always be posting whether or not we have more starry nights based on the weather, and we'll send out those announcements either through email, so make sure you're on our mailing list, or through social media, so on Twitter and our Facebook page. So we always post them on there as well. So keep in touch, and remember to keep looking at the skies. Thanks for tuning in tonight.
And thank you to the moderators who helped us, Disha from the Royal Astronomical Society, and Kyle and Zena as well. Thank you so much.
And thank you to Kelvin for tuning in at the beginning, our special guest.
That's right. Thank you, Kelvin.
And Dr. Joanna Wu, thank you for joining me tonight on such short notice. I appreciate that.
Yeah, this was fun.
It was fun. Okay.